Welcome to the second lecture related to the topic ordinary differential equations. In the last lecture, we introduced ODEs from an analytic approach. We wrote a lot of formulas. Today, we will see a geometric interpretation. And to do that, we will concentrate in first order ODEs. So the first thing is to write down first order ODEs in a specific way, which is this way we can see here. Okay? Whenever I have a first order ODE, I will have an expression that depends on the unknown, the independent variable, and the first derivative, because it's a first order ODE. And the first thing I need to do with that equation is to rewrite it in this way. So this means that y prime t must be isolated in the left-hand side of the equation, and everything else will be written in the right-hand side. So for example, if I have a differential equation like y prime t plus 3 times yt equals the exponential of t, I would first rewrite this as y prime t in the left-hand side equals, and everything else that depends on t or that depends on y is written in the right-hand side of the equation, so leaving me with this expression. So everything here in the right-hand side depends on t and y. That's why we call it f of t y. Okay? Now, using this way to write down first order ODEs, we can make a very nice geometric interpretation of what is an ODE. And it's the following one. Let's say I have the time axis here. So let's say this is some point t. And let's say this is some point y in the y-axis. So this is my point called ty. Okay. Now, when I try to solve the differential equation, I'm trying to find a function that goes through this point. This function is called yt. And solving the differential equation is finding out who is this function. Yeah? Okay, now how can I do that from a geometrical point of view? Well, let's use the information we have here at this formula, okay? This formula is telling us that at point t here, y prime is equal to f of ti. And I can compute f of ti. Okay, the unknown is y prime t. So what I'm trying to say here is that at this point, I can compute the tangent line at this point, because y prime t is the slope of the tangent line, and the slope of the tangent line is equal to f of ti. So this slope, if this is 1, this slope is f of ty. So, for example, if I know I am at point t equals 1, y equal 2, I can come here and substitute t by 1 and y by 2, and I can compute this value, and this value is telling me the slope of the tangent line. So what I'm trying to explain here is that an ODE, an ordinary differential equation, is nothing more than a vector field. Whenever I'm given a first order ODE in this way, at any point ti, I can plot a vector. So that's a vector field. And what's the solution? What's a solution of the ODE? A solution is a curve that is tangent to this vector field at any point. So a solution of the ODE is going to be equivalent to what we call an integral curve, which is nothing else but a curve tangent to the vector field at each point, yeah? So maybe you will understand better here, okay? Here I have an ODE, and this ODE is giving me at any point I select. For example, here we selected this point, okay? At this point, I can compute the value of ft(y), and I get this vector, and I can compute it just using 1 versus f of ty, and this is the slope of the tangent line. So here in red color, we have the solution of the differential equation, which we can see that it is tangent to the vector field everywhere, yeah? You can see that this red curve is tangent to the vector field. So this is the geometric interpretation of first order ODEs, and it's a very important concept. Now, an initial value problem can have many solutions. I know that in the last lecture I said that if I have an ODE and it's first order and I have one initial condition, then I have an initial value problem, and that might have only one solution, but I'm not sure. It could have more than one, or maybe have no solution at all. So we really need something that will tell us if an initial value problem is what we call a well-posed problem. When an initial value problem has a solution and it is unique, we say it is well-posed. In Catalan, we say it is ben plantejat. Problema de valor inicial ben plantejat. Now, what we will see is a theorem. We will not prove it, but this theorem will allow us to guarantee the existence and uniqueness of the solution for first order initial value problems. Let's see this theorem. It is called Picard's theorem, and it says that if you have an initial value problem where the ODE is written in this specific way we were talking about in just a few seconds ago when dealing with the geometric interpretation, and we have an initial condition of the problem. Recall here is the first order ODE. We give one initial condition of the problem. Then Picard's theorem tells us that if this function f here, this f, and the first partial derivative of f with respect to y are continuous functions, where? Well, in a rectangular region that contains the initial point, where the initial condition is given. So if we see here the plot, this is the point t0, y0, t0, y0. The theorem is telling us that if f and the first partial derivative of f with respect to y are continuous in this rectangular region that contains the initial condition of the problem, then there exists an interval, which is this interval here, okay? Exists this interval here, where we can guarantee that the initial value problem has a unique solution, okay? So this theorem is giving us some hypotheses that when they are verified, then we can guarantee that the solution is unique. Now we will see some examples where we will try to apply this theorem and see if we can conclude whether the problem has or not a unique solution. And at the same time, we will explore the geometrical interpretation of ODEs. Let's start with this example. verify that the initial value problem y prime t equals y plus this initial condition has a unique solution. Well, let's see if we can verify that. What we can do is check whether the hypotheses of Picard's theorem are met. Now, in this case, who is the function f of ty? Is this f of ty is whatever is in the right-hand side when the ODE is written as y prime t equals something else. So in this case, f of ty is just this function y. Okay, now I know f of ty is y, and the initial condition is given at t0 equals 0 and y0 equals 1. Now, I know that this function, f of ty equals y, is continuous all over the domain because it's a polynomic function. And the first partial derivative with respect to y is a constant value, so of course it is continuous everywhere. So they are continuous functions everywhere, also at the initial condition point. So we can, using Picard's theorem, guarantee that this initial value problem has a unique solution, whatever is the initial condition given in this case. Okay, so in fact, there exists a unique solution regardless of the initial condition of the problem, because both f and the partial derivative of f with respect to y are always continuous for any value of t0 and y0. This is the geometric interpretation of this ODE. The blue vector field represents the ordinary differential equation, and the red curve is the specific solution when using the initial condition y0 equals 1. We can see here that maybe we can change the initial condition of the problem. Maybe we want to use the initial condition y0 equals 5. That means that I want to go through this point when t is 0. I want y to be 5. Well, in this case, I would have a different solution. The solution, remember, that is always tangent to the vector field, yeah? So it will be a different solution, but always tangent to the vector field. Trying to do my better here. But the idea is that you can see here that you can choose any point you want in the vector field, and there is always one solution, and it is unique. Okay? That's what we proved with Picard's theorem. Now another example here. Now we have an ODE that looks like this. Y prime equals t divided by y. And the initial condition is given at the origin. And it says here, solve using Maple. And the question is, does the result contradict the existence and unicity theorem? Well, let's see. We use Maple here to solve the initial value problem. And, well, it looks like when we solve the problem using the initial condition, we get two different solutions. So it really looks like that the solution is not unique because Maple is giving us two different solutions. And we can see the plot here. What we can see here in red colors are the two solutions that are obtained when the initial condition is y0 equals 0. And if we look to the vector field, it really makes sense that there are two solutions going through the origin. Yeah. Here the vector field is showing us different directions, yeah, and we can see that at the origin there are two possible solutions. One solution is the one that is coming from here, the other solution is the one that is coming tangent to the vector field from here. Now the point is, if I start here, if I start at the origin, if my initial condition is given at the origin, I don't know which one is the solution. It's not unique, yeah? So in this case, if we try to apply Picard's theorem, you would see what happens. Well, when I try to apply Picard's theorem to my PDE, which was this one, now this is f of ty in this case, and of course this function is continuous everywhere but not when the denominator is 0, so not when y is equal to 0. And the same is going to happen with the first partial derivative with respect to y. This function is continuous everywhere but not when y is equal to 0. So Picard's theorem does not guarantee the existence and unicity of the solution for the initial condition y0 equals 0. The problem here is this 0, yeah? The problem is the value of y. So since here the hypotheses of the theorem are not met, we cannot guarantee what's going to happen. Yeah, so we cannot guarantee if the solution, the theorem can only be used to check if the hypotheses are met, and when the hypotheses are met, then it says the solution exists and is unique. But here, since the hypotheses are not met, we cannot conclude anything. What we did is to use Maple and check, and we found out that, okay, the solution exists, but it is not unique. This is a remark about this ODE. We can see here that the solution would be unique if the initial condition is given at points where y0 is different from 0. For example, this value here could be used as an initial condition and the solution would be unique. Or this point here, which is also given at t equals 0, but the value of y is 1. So this has a unique solution. But if we reach the value y equals 0, or we want to move away from y equals 0 because we use that as the initial condition, then the solution is no longer unique. A last example. Here, the ordinary differential equation is this one. The first thing we need to do is to rewrite it properly. We need to isolate y prime t at the left-hand side. So this equation will look like t squared cosinus of t plus y, and then everything would be divided by t. Okay, this t that comes from here. Okay, so this term in the right-hand side is f of t y. Now, in this case, when I look to this function, I see it is continuous everywhere, but not when t is equal to 0. So we will see that this function and its first partial derivative with respect to y are both continuous everywhere, but not at t equals 0, because t is dividing in the denominator. So therefore, since for t equals 0 they are not continuous, Picard's theorem does not guarantee anything about the existence and unicity of the solution. If the initial condition was given at a point different from 0 here, then we could guarantee the existence and unicity because Picard's theorems could be applied. Here we can see the geometric interpretation of what we concluded. We can see here that any initial condition given, for example, here at a value of t that is different from 0, the solution is unique. The curve that goes through this point and is tangent to the vector field everywhere is a unique curve. It exists and is unique. And you can choose any point in the vector field here to impose the initial condition of the problem, and you will have a unique solution, but not when t0 is equal to 0. any initial condition of the initial value problem where t0 is equal to 0, which is this, all the points lying on this line here, will lead to an initial value problem which has not a unique solution. Okay, that's what I wanted to explain today about the geometric interpretation and Picard's theorem to try to check the conditions, and in case we satisfy the hypothesis, the theorem can guarantee the existence and unicity of the problem. Thank you very much. Bye-bye.